Another video of AS Biology revision with Mr Phillips of the first year of AQA or OCR Biology. Today's topic is going to be water, so it's video 1.9 for me, and we'll look at the important properties of water and why particularly hydrogen bonding is important in these properties of water, and then briefly at inorganic ions. So water is very common. Obviously, we're aware of what water is, but we also know it is essential for life. We should know from GCSE that water is 2 molecules of hydrogen bonding to 1 molecule of oxygen, covalently bonded. It's a liquid at room temperature. It's odorless, colourless and tasteless. So why on earth is it so important? So it could be quite a common sort of 6, 7, maybe even 8 mark question. Why is water so important? And that's what this this video is going to help you do. So first of all, we need to understand what hydrogen bonding is. So if we have a look at this drawing now, I've got a pretty hideous red background, but that should hopefully help things stand out for us. So the hydrogen bonding, basically, if the X represents oxygen and the Y's represent hydrogen there, what we find with atoms is there isn't just the electrons in atoms when they do covalent bonding, which is the sharing of electrons, they're not equally shared. So there's an unequal distribution of electrons. So what tends to happen, because oxygen is the bigger atom, it tends to pull in it's got a bigger nucleus, a bigger positive charge, it tends to pull in the electrons from hydrogen a bit closer to the oxygen atom. So what we say is that makes it slightly more negatively charged, and the hydrogen becomes slightly more positively charged. So these symbols at the side of that have just appeared then represent this. So this is called the delta positive symbol for hydrogen. There's one there for that hydrogen, and then this is the delta negative symbol for oxygen, which means it's slightly more negative because it's pulling the electrons closer towards it. So what happens is we get this sort of weak bonding happening between the delta negative charge of the oxygen and the delta positive charge of hydrogen. So you get very, very weak bonds called hydrogen bonds, which constantly make and break all the time as water molecules are moving. Now individually they are very, very weak, but when they form in thousands and millions, then they become very strong and useful bonds. And it doesn't just have to be water. Any molecules that have slightly positive areas and slightly negative areas, delta positive and delta negative, will have hydrogen bonding. So we talked about in one of the previous videos, we talked about hydrogen bonding in cellulose chains. So that would be again due to positive and negatives. Often it is due to hydroxyl groups, OH groups and H+ groups. So there's no way of showing it up here. So just again, very, very same sort of thing I just mentioned a few moments ago. But you've got here just the hydrogen with the delta positive, the oxygen with the delta negative. Okay, so it just means slightly positive, slightly negative, and then you get a chain of hydrogen bonds happening between the different water molecules. So in pure water, we get hydrogen bonds that form this network of atoms. They constantly break, constantly reform. So nothing everlasting, or they're very temporary. It makes it difficult, however, for an individual water molecule to escape. So it's as if the water molecule is trying to escape at the top, another hydrogen bond grabs it, another hydrogen bond grabs it, another hydrogen bond grabs it, and that's what gives water its relatively high boiling point, and what we call a high specific heat capacity and latent heat of which we'll talk about in a few moments. Hydrogen sulfide is H2S, which is very similar formula. Think about water, H2O, H2S, just one atom different really. It is normally a gas at room temperature because it doesn't form hydrogen bonds, whereas water, obviously hydrogen to oxygen, does form hydrogen bonds, and that's normally a liquid at room temperature. When the water cools, what happens is molecules will lose their energy, they stop moving so much, and then the hydrogen bonds sort of fix in place, and that makes water become a solid. So hydrogen bonding pretty much is essential for all of the properties that we're about to talk about now for water, that makes water an essential molecule for life. So what you would expect then, if we look at water, is you might get a question on why ice forms. Now, I'll only ask you a question on that if it's about the environment, but it could obviously still come up to about aquatic environments and habitats in that respect. Now, what you would expect with most materials is that as you decrease the temperature, the density, as this red line is now showing, will increase, and it will keep increasing until obviously eventually, I suppose, it would level off. It won't get any colder, but it will keep going up like that. Water, however, is different. So if we start here at this 12 at this end of the graph, as with other molecules, as you decrease the temperature of water, so it gets colder, water gets more and more dense, but then you hit this magical sort of figure about 4 degrees, whereas if you go below 4 degrees and down to like 0 and a couple below 0, the density of water will decrease. Now that is absolutely essential, because what that means is it means that ice, as you see in this picture at the top here, will form above water in aquatic habitats. So this scuba diver is under the ice but swimming quite freely in the water, and you can see here are the ducks on a pond there standing on the ice, and they're obviously safe. Why is that useful? Because that means it insulates the water below, keeping it warmer for the aquatic organisms, and also it means it's very unlikely the water's going to freeze, because the ice keeps the water below it warmer, and therefore it's not going to freeze all the way down. It has to be a very, very cold winter to get that happening. Why does ice get less dense, or water get less dense as it turns into ice? If you have a look at these two diagrams at the bottom, you can see when water is just water, the molecules of particles of hydrogen and oxygen are very close to each other. When it becomes ice, however, because of hydrogen bonding, they hold the water molecules in place, and there's gaps that appear between the water molecules as it's held in place, so you get less mass per volume. So effectively then, hydrogen bonds restrict the movement of water, and that obviously means that the ice can then hold in place. Also, when you talk about increasing temperatures, hydrogen bonds restricts the movement of individual water molecules, and that means that you need quite a lot of energy to break those bonds between the water molecules and to allow the water molecules to move freely. So even with dramatic temperature change, if you think about it, if you went from 10 degrees C up to 90 degrees C, water would still be water. It wouldn't have become a steam or a gas at that point. So you need a lot of energy to break the bonds and cause evaporation. And so the vital part of our living point is this, because we use it for many things. So here's another, so this, therefore the importance of that is it gives water a high specific heat capacity. So a term you should know from GCSE physics. Water's got a specific heat capacity of 4.2 joules per gram per centimeters centigrade, Celsius. It takes 4.2 joules of energy to heat 1 gram of water by 1 degrees C. I think that should be a kilogram. This is really high, okay? And the point is that being really high, it means that water temperature doesn't change that easily. And this is quite important, as you can see. If you have a look at this graph, even with this high specific heat capacity, we're starting to see an increase in temperature of the oceans, as shown by this graph here. Now, the oceans are very, very stable temperatures, and that's absolutely essential, because what will happen is if the water temperature, and this one doesn't actually say oxygen, it shows you ammonia, but it's the same effector. If the water temperature increases and our temperature of water increases due to global warming, the amount of oxygen that the water can hold will decrease, and that is already showing some areas of concern in our oceans where we're having oxygen depleted zones. Then we've got, because again of the hydrogen bonds holding all those water molecules together, constantly reforming and breaking and reforming, it also means we need a lot of energy to turn for the latent heat of vaporization, which means the energy required to turn liquid into a gas. And that's really useful as living things, because what that allows us to do is use evaporation to get rid of heat energy from our body. So we can use it for sweating in mammals, and we release sweat onto our skin. That energy, that high amount of energy causing that liquid to evaporate, is then lost and it cools us down. Animals like dogs will pant and things like that to keep themselves cool, and as the water evaporates, it extracts that heat from our bodies. And obviously it shows you the amount of energy that is used in the atmosphere to cause evaporation, to make rain clouds. Also potentially explains why we might in the UK and other parts of the world get wetter winters and wetter summers even in the future, because if global warming increases the temperatures, there's more evaporation of water from the sea. That water will move inland before it condensates and rain more onto us. Next one then is very similar, latent heat diffusion. So this is, it will take a lot of energy to change ice into water, and that means again, it's stable environment. So if you're in colder places and you've adapted to those colder places, you shouldn't get the ice melting all the time. Obviously we have an annual melt of ice, and obviously because we are increasing the global temperatures, we're starting to see this, which just shows how much energy we have trapped in our planet. Water is an important metabolite. So what I mean by this is it's part of a reaction, part of a metabolic reaction that is causing, a metabolic reaction is the sum of the reactions in our body. And we've talked about this in earlier videos. If you think about water, we've talked about hydrolysis reactions, where we add water in order to break a molecule apart or to put two molecules together. We do a condensation reaction where we remove water. So water is essential in that reaction. The reactions of respiration and photosynthesis, which you do in year 2 or year 13, they are obviously involving water. If you think about the GCSE equations you learnt there, and that's essential in those vital living processes. And when we've talked about ATP, which you can look at year 13 videos, if you want to look at ATP, look at the first year 13 video. That also shows you water is essential to release energy from ATP. There's something called cohesion tension theory, and this is the idea that water molecules will stick together to each other. So you can have a look at this picture on here of the what looks like a spider on this water, walking on water effectively, and we think, well, how can water do that? Well, it is possible to do it. You can see here there's looks like a paper clip in some water there that's floating. The reason it is possible is obviously because of the large surface area of the insect, but also because the water has something called surface tension, and that is because the water molecules stick together. So that is called cohesion. So sometimes you might hear like a commentator in a sports game saying they're a cohesive unit, and that is because they're working together. Well, cohesion is the idea that water molecules will stick together, and also that means that you can use them in plants to get high way up a plant. So transpiration of a plant, let's say a California redwood tree, which might be 200 meters in tall, it can pull water up the xylem all that way because of cohesion tension, as well as some good adhesion as well. But cohesion tension is the water molecules sticking together. Water's got a central role as a solvent. So think about it, a lot of things dissolve in water, and that is absolutely critical. It has to be polar like water that will dissolve. Obviously some things won't dissolve in water, but what this allows is different reactants to mix together and to react. If we didn't have water inside us, we wouldn't have this solvent, we wouldn't have chemical reactions happening inside our cells. Also water, think about it, your bloodstream carries things, it's vital in your transport system, it aids diffusion, and so on and so on. So very, very useful for that reason in your body. Now, the last thing then, once we move away from water, is you need to know about some inorganic ions. Now, I tend to sort of think with this is that you need to sort of be aware of this, but as you go through your A levels, it'd be worth you sort of coming up with a sort of a tick list of these are the ions we've talked about, and this is what they do. So positively charged ions are called cations, negatively charged ions are called anions. I don't think that's massively vital for you to learn for A-level biology, because it's not chemistry. However, obviously term could be used in an exam. So just give you some examples. Sodium is often used in nerves. You'll talk about something called the sodium potassium pump in nerves, but it's also used in facilitated diffusion and co-transporters, which you'll meet in year 12 as well. Calcium is used in the synapse, and it's also used in muscle contractions, so it's absolutely essential in our diets and obviously to keep healthy. We've got chlorine then, which is used in something called the chloride shift, and chlorine basically helps with oxygen loading in the red blood cells. And we've got phosphates, which are involved in our DNA, and you can do something called phosphorylation. So ATP is obviously got adenosine triphosphate. So energy, or we've got basically a chemical that is our energy, is adenosine, which is and then triphosphate, which is 3 phosphate molecules, and it's the attachment and removal of a phosphate molecule that eventually gives us the actual energy we need. And then what is an inorganic ion? Well, basically it means it's something that doesn't actually contain carbon. Inorganic means no carbon. So if you do chemistry A level, you do inorganic chemistry, it means non-carbon chemistry, because carbon atoms are found in all organic materials. All living things contain carbon. They have specific roles in cells. The one that you should be familiar with is iron in hemoglobin, and basically when the ion, so Fe2+, attaches to oxygen, it temporarily becomes Fe3+, and then that's a reversible reaction, so that one can go forwards and it can go backwards, obviously to pick up the oxygen at the lungs, drop the oxygen at the respiring tissues. And then H+ is an ion, obviously, that is linked, hopefully, to acid, and the acid is actually, an acid is a proton donor, H+ donor, so it releases it, and obviously alkalis or bases are OH-. So I hope that's been useful for you, and I'll see you again next time.